All right, so good morning everyone and welcome to this last tutorial of the soft matter lecture. Before we start, let me introduce to you a final book that I recommend warmly. Here it is. So it's a book called Soft Interfaces, and it is in fact the lecture given by Dejean at the Dirac Memorial where I received the prize. So it's a very interesting book. It's very thin. It's full of plenty of little examples with potential research for the future. In fact, plenty of open questions and simple scaling arguments, but at the same time, very deep thinking. So I would really encourage you to have it for Christmas and read it. Now we are dealing with the last tutorial, which is about the famous dynamics of polymers. And in particular, there is the reptation scaling that was part of the reason why Dejean got a Nobel Prize. So here is the article about the reptation. Basically, is creating or describing the motion of one polymer chain as a motion of a diffusive snake-like object that is reptating among a frozen ensemble of neighbors that creates a tube around the chain, and the chain is diffusing inside, and it is by a refined argument is able to obtain a realistic exponents for the relation between the viscosity of polymer melts and the length of individual chains. So I encourage you to have a look at that. There are also works by Doy and Edwards about that. And today we will generally talk about polymer dynamics. First of all, I would like to remind you briefly Langevin dynamics that you all know. Then we will describe the Zim and Rao's models for the motion of small polymer chains, and then discuss the relaxation of internal degrees of freedom in a chain before scaling briefly the reptation argument by Dejean at the end. Okay, so this is the program for today. Let me switch to the whiteboard now. And of course, feel free if you have any question to send them by email because you are not present today. All right. So just a minute. All right. So first of all, the reminder about Langevin dynamics. So we are dealing here with polymer chains, but we will assume first that those polymer chains, they are coiled with a certain radius and that we can describe them as a certain spherical object with a certain radius r and a certain mass m. Okay. This spherical object is placed inside a viscous fluid with a certain viscosity eta and at a given temperature T. Right, and we will describe the motion of the center of mass of that polymer chain by introducing its coordinate r of t, which is a function of time starting from an origin. All right, and we will assume that this polymer is subject to two main forces. First of all, a viscous drag from the solvent, and secondly, some random forces created by the collision of all the particles constituting the fluid around. So this is very generic to Langevin dynamics here. And so we assume that in particular there is this deterministic dissipation force which scales like the speed, which is inversely proportional to the speed, and psi here is the damping coefficient. For a sphere in a viscous solvent, it's provided by that formula, the Stokes one. And then we have also some random forces, thermal forces, that allow to describe the action of individual collisions by all the molecules from the solvent. All right. So we start. Let us express the properties of that random force. So we will assume that on average, this force is 0 because you have an isotropic and homogeneous system. The collisions can come from every direction, and on average, they should not create any drift at equilibrium, which can be written this way. For every coordinate, we will have the average, which is 0. Then we have the correlator, which is the next one, and the correlator between two coordinates at two different times, let's say J coordinate and times t, which can be shifted by any tau you wish, and this can be all averaged over the time. We will assume that the force is delta correlated in space and time. So there is a constant factor. You want a Kronecker on the direction, or you want to have only correlation in a given direction, and then there is no memory. And so only if you consider an equal time for those two forces, there is a correlation. Otherwise, they're completely uncorrelated. Of course, this is a way of modeling things. If you have an experiment that is able to resolve very small time scales, then you have to refine this by adding a distribution with a certain width and in time and a certain memory. All right? But for our purpose, this is sufficient. And all the unknown part is put in this constant that we will determine. Right? Okay. So this is for the correlator of the noise. Then let us write the equation of motion. Well, we have inertia. So this starts with the acceleration of the particle, the second derivative with respect to time. You have on the other side the forces, the damping plus the random force. That's the very generic equation of motion. As we can see in this equation, on average, you could write it this way. If you average over time, plus 0, as we said above. And thus, there is a natural time scale that appears. Let us call it tau as well. It's different from the previous one, but this is the time scale for relaxation of inertial effects, and it is provided by the ratio of the mass and the damping coefficient. Right? So that's the relaxation time for inertia. After this time, you can basically in the equation neglect that term and say that you have an overdamped dynamics. All right? So we can estimate that time scale for relaxation is the mass. So the mass is the density times the volume, all right? R cube we have. And we said that the coefficient is something like that, all right? So it scales like, let us remove all the unnecessary stuff. So there is this pi that vanishes. Then you have rho eta r squared. And then as a prefactor, we are left with something like 4 over 18, which is 2 over 9. Okay. And in terms of numbers, the density we will deal with typically something which is close to water. The radius we estimated in the first tutorial, the typical size of a polymer chain was 20 nanometers when we were constructing that by saying it was that the square root of the number of monomers and the size of a monomer, and we said this is typically 0.2 nanometers, 2 angstroms, and this is typically the square root of 10 to the 4. So it was 10 to the 2. All right. So that's a medium number. You can have other values. So here it was 20 nanometers, so 2 10 to the minus 8. And the viscosity, something like 10 minus 3 in water. And then you have this 2 over 9. So basically we can forget those typically. And we are left with 10 to the 6, so 10 minus 10, which is 1 angstrom. Sorry, which is 100 picosecond. Okay, so that's the typical time scale, after which you can completely neglect inertia in this problem. So it's pretty obvious that it is a small time scale, comparable to molecular or atomic time scales, and therefore you can really forget inertia in this problem if you are dealing with millisecond or second-like dynamics. All right. Okay. So now let us integrate formally the equation of motion. So I remind you that it was provided by this equation, and so we will divide by m everywhere. And so this is what we get. Or let me even write this as the velocity. So dv dt is equal to minus v over the time scale we introduced for relaxation of inertia, and then we have f over m. So first of all, we can solve the homogeneous equation, which is this one without any noise forcing the dynamics. And this is a simple exponential behavior. So VH is some kind of constant. Let me call it B times the exponential minus T over tau. All right, and now we will do the variation of the constant. So, and assume that the solution of the real equation is this one, but B being allowed to be a function of time. So now if I take this velocity form and plug it into equation star here, I end up with B star exponential minus T over 2 minus B over tau exponential minus T over tau is equal to, and sorry, this is a velocity, so I should put arrows everywhere. Excuse me for that. And on the other side, we have minus B over tau, which is the homogeneous part, cancelling the one on the other side here. And you have F over M. So the homogeneous equation cancels out by construction, and therefore we are left with the following equation: B star, or B dot, sorry, is equal to exponential plus T over tau times F over M. Okay, this is at time T. And thus B will be the primitive of that guy. So let me integrate over T prime. I don't specify the bound for now. F of T prime divided by M. All right, and we can anyway, without loss of generality, assume that the velocity is equal to 0 at time t equals 0, which allows me to specify the bound here so that the constant cancels at initial time. So that's the initial condition here. Therefore, the velocity altogether reads 1 over m integral of this guy, and there is this minus t over tau that appears because the total velocity is b times the exponential in time t. All right, so this is the formal solution of your equation. I cannot do more than that because this guy is a random object. We know its distribution, at least we know the two first moments of this distribution, but we cannot predict deterministically its value, so we cannot have more than that for V. However, we can have properties of the average of V, the mean square of V, and so on and so forth, and we will discuss that in a minute. So this is for V, and then we want to go to the position, and we have to remember that V is in fact the first derivative in time of the position, and therefore the position will be the integral of that guy, again, 1 over the mass and then I just shift the variables in the integral. So I basically integrated that, and also I have assumed an initial condition saying that I'm starting from an origin at t equals 0. This is without losing any generality again. It's just the decision of what is the origin in this problem. So I end up with the formal solution of my problem. The trajectory of the Brownian particle is provided by some kind of convolution, as you can see here, of the kernel of your equation and the source term, which is the force exerted on the particle. So it's a linear response or green-like response, if you wish. All right. So now that we have that, we can discuss the properties of, let's say, the average and the variance of that trajectory. So let us start with the mean square velocity. So I guess this is question number 5. So here we go. The mean square velocity at time t, well, is simply this object. And which is the average of, well, we know already the velocity. It's provided where here. So it's 1 over m. So you have 1 over m squared. And then you have 2 times this integral. Then the same with t second. And the exponential t second plus t prime minus 2t over tau. And then you have the scalar product of ft second and ft prime, or the reverse. All right. So this is the average of v squared, and I can invert the integrals and the average symbols because they are all linear operations, and end up with the double integral the kernel is a deterministic quantity, and then the correlator 2 times of the noise of the force, the thermal force. And so remember, we've expressed the properties of f at some point. We've said that for 2 independent coordinates, I and j, and 2 different times, we know the correlator is provided by a constant, delta ij, a Kronecker on the directions, and delta tau to express the fact that we are delta correlated in time. So this is the sum over I, 1 to 3, of fi with the same I here. And this is A times the correlator in time, according to what we just said. So altogether, there is a factor 3 because this is independent of I. And so we end up with 3 over m squared times A. And then you remove one integral by equating t second and t prime. All right. Okay, so then we can do a little change of variable. We can introduce 2t prime minus 2t over tau as a new variable u, du being equal to 2 over tau dt prime, which allows me to rewrite this quantity as a function of, so there is a tau over 2 appearing in front, then you have this du exponential u. All right, and the bounds, when t prime is equal to 0, we have minus 2t over tau. And when t prime is equal to t, we have 0. Okay? And therefore, v squared at a given time is equal to 3a tau over m squared. And the exponential becomes 1 minus the exponential of minus 2t over tau by integrating this guy. All right, and so in particular, we know that tau is m over psi. And so we found the average of v squared at a given time. Said over either you average over time or you average over realizations, which is equivalent at equilibrium. And so now let's talk about equilibrium. Equilibrium is reached when you forget your initial conditions. So when time goes to infinity, and this means that v squared at equilibrium becomes equal to 3a over 2m psi. That's coming from our results. But at the same time, we know that at equilibrium, the average of the kinetic energy, which is this guy, should be provided by kBt over 2 per unit of freedom, per degree of freedom, sorry, and we have 3 directions in space, so something like that. That's equipartition. All right, so we have those two relations that should be consistent one with another. And so it provides you that 3a over 2m psi should be equal to 3 kBt over m. Right? And thus, mass is irrelevant. And you end up with the fact that a should be equal to 2 psi kBt. And this is a very important relation that is called the fluctuation dissipation relation. This guy is the amplitude of the noise, because this is the amplitude of the correlator of the force that we didn't know so far, but now it's specified. This guy is the dissipation, is the drag coefficient, and this guy is temperature. Okay, so there is a correlation from this expression between the dissipation and the fluctuations, and temperature is playing the connection. Right? Okay, so I'm sure you were all familiar with this, but now we have the notations, and we will assume that this is valid for the motion of the chain as a whole, for the center of mass motion, if you wish. So that was the zero part. Let us attack now the first part of the tutorial, based on this reminder. And we want to discuss the Zim and Rao's models that I will define. So now we consider realistic situations. We are in a viscous liquid, even like water, if you wish, and we look at relevant times for polymers, biology, soft matter, and plenty of things. And we are at time scales that are much larger than the inertial time scale, right? Millisecond-like, let's say. So it means that in this equation here, we can forget inertia. And we are left with simply the dissipation, I mean the damping, balancing, the noise, okay, the fluctuation term. So the random force V. And therefore, we end up with simply this expression for the velocity, and thus R being the integral over time of this guy. So we have f of t prime 1 over psi, and we can again fix the origin such that at t equals 0, the position is at origin, so R equals 0. So it's a much simpler situation here. And we found the formal solution. Again, this guy is random, so I cannot say more than that. I only have statistical properties for F, so I only have statistical properties for R, but I cannot find a more analytical expression than that. All right, so let us quickly recover the diffusive law here. So R squared at a given time will be given by the square of the above equation. So the scalar product between the noise at 2 times and then the average as before, right? And just as before, this is then 3 times A times delta Dirac of time. So we end up with 3A over psi squared as a function of one integral in time, which is the integral of 1, right? So the result is the following: 3A over psi squared times t. And we can express that further, recalling that A has been obtained by the fluctuation dissipation theorem with the inertia present initially. So 2 psi kBt. Right? So we recover the fact that the mean square displacement is equal or is proportional to time. So this is a diffusive-like process, and we can further introduce the diffusion coefficient by recalling that R squared is equal to 2 times the dimension times the diffusion coefficient. Indeed, you see here that the factor 3 that comes here, so it's 2 times 3 here, and the 3 comes here from the integral in space, so the sum over all the directions in space, so it's really the dimension, in fact, okay? With the definition of the 1D diffusion coefficient being simply kBt over psi, and in my language here, with the Stokes equation. All right. So this is what we call the Stokes-Einstein relation, connecting the diffusion coefficient, temperature, and dissipation. All right, this is for a spherical object of radius r. Now we have to discuss a bit what is really the size r. So we have two approaches historically. There is one proposed by Zim, who says that in fact, what we should take as r, well, is the radius of gyration. So for now, I neglect completely the distinction between real solvent solutions and so on, or ideal random walks and the square root of n, because I'm not really interested in the discussion on the exponent. I'm rather interested in the discussion of, is the polymer chain as a whole, as an object of size r, dragging the fluid with it, or is it each individual monomer inside that is dragging the fluid, and they are all independent, okay? And you see what I mean. So for the Zim situation, it has been proposed that, in fact, this moves in a solvent at a certain velocity, and the solvent goes around inside. Basically, the solvent is moving together with the monomers, and so this is acting as a hard disk, hard sphere, as a rigid object. There is no fluid motion inside the polymer chain. That's one assumption. We could discuss it later. So if you do so, you can rewrite the ZIM diffusion coefficient as kBt over 6 pi eta A times 1 over square root of n. And if you want, I can introduce that guy as d0 times 1 over square root of n. d0 being the diffusion coefficient of a single monomer, right? And so we can estimate, by the way, d0 here, which is kBt, so 4 10 to the minus 21 divided by 6 pi. So we will discuss the prefactors after. 10 minus 3, and one monomer is 2 angstrom, as we said. Okay, so 2 10 minus 10. All right. So 6 times 3 is 18, or 20 times 2 is 40. So in fact, you can replace those guys by a factor 10 only. And you end up with what? With 10 minus 12, so it's 10 minus 9. Meter squared per second. Okay? So that's the first number we are interested in. And so now the ZIM one, well, is much smaller. And if we take n is equal to 10,000, as we did in the first tutorial, well, we are dividing by 100, so it's 10 minus 11. So it's much smaller than the motion of an individual object, of course. Okay. That's one proposal. In fact, we will see and discuss that later, but this proposal is valid for polymer chains in solution. For instance, if I'm really in a solution with only one chain, it's a dilute solution. Here I have solvent molecules all around and no other chain. One can show that by hydrodynamic interactions, this polymer chain is dragging fluid with it, and it behaves mostly as a big sphere that is rigid with no fluid flow inside. Okay, so that's a good description for solutions, and here dilute even, because I have only one single chain. Okay, but there was another approach that is attributed to Rouse that is very different, that says that, well, in fact, a polymer chain is an assembly of spheres. And each of those is subject to a certain hydrodynamic force, if you want. If I just write the velocity of one object here. So in this picture, Rouse say that the diffusion coefficient should rather be kBt of 6 pi eta r, with r being Na. The total size, I mean the hydrodynamic size, is simply n times the hydrodynamic size of one monomer. So written this way, it's the diffusion coefficient of one monomer divided by n. And so since this is 10 minus 9, with our values, we are, times 10 minus 9, which is 10 minus 13 meter squared. So again, much smaller. And this is in general valid for a melt, where you have actually plenty of other polymer chains, and here every monomer is considered as a friction-like object and will drag fluid in this view around. Okay, so those are the two approaches proposed historically. So now let us move to the internal degrees of freedom in that problem. All right, so far we have discussed the motion of the center of mass of a polymer chain. And we said, well, in fact, in this sphere, there is a chain, but I don't care about the details of the positions of all the monomers. I will describe it as a sphere, and it has a certain position and a certain velocity. And I will assume that there is some drag coefficient, either because the fluid goes around that object, or because it goes also a bit inside. And this is the Rao's discussion. But anyway, I can put all the details of that into one coefficient, which is psi, which amounts to defining what is the hydrodynamic size R. Okay, this is what we've done so far. But in fact, the polymer chain could experience some elongation. We know that you can pull on it, for instance. So due to fluid flow, due to fluctuations, whatever, you can have some stretch-like object and not coil-like object. Therefore, in this description, we are neglecting the inner degrees of freedom. Okay, and so in fact, there is a time scale associated to the relaxation of that polymer chains toward a more typical configuration, where you have a lot of microscopic states corresponding to it. Okay, and so therefore we need to have a model to describe the dynamics of the inner degrees of freedom and not only of the center of mass, which is the outer degree of freedom, if you want. So the most simple model for that is called the elastic dumbbell. It says basically that you can say that a chain is in fact a spring connected to two masses, M1 and M2. Basically, you can always describe your chain as something like blobs, two blobs, and when they are separated, the spring is under tension, and when you want the spring to be at rest, you want those two to come back to a single position. Okay, so this is the first way of describing one anisotropy in the problem, one extension, one internal degree of freedom. Okay, so to do that, you basically take half of the material on one side, a spring, and half of the material on the other side. And you assume that this guy is submitted first to a viscous solvent and the temperature outside, but also to random forces that are independent from each other. So now you have a two-body problem. You have a kind of molecule with a spring in the middle here that is put in a fluid, and every of the two sides are subjected to Langevin-like forces. And the question is, what is the equation and the behavior of such an object? All right. So for that, we need to introduce a stiffness and an extension R, which is simply the distance between the two positions of the two centers of mass, those sides. All right. And we assume, of course, that F2 and F1 have exactly the same kind of properties as what we have introduced for F before, mainly a zero average and a delta correlation in time and space. When I mean in space, I mean in directions. Okay, X doesn't talk to Y, which doesn't talk to Z either. All right, so let us first describe what should we put into K, the spring constant. So again, let us involve equipartition theorem and say that now we have a degree of freedom, and at equilibrium we would expect the average of the potential energy, the elastic energy, to be provided by the number of dimensions times kBt over 2. Okay, so this implies immediately that we have a relation between K, the number of monomers inside the chain, and the temperature. Because we know that for a real polymer chain, let's take it, sorry, not real, ideal for now. Let's write it this way. So we are not, again, we are not discussing ideal versus flowy behaviors, because there are dedicated studies for that in the past, tutorials. Here we want really to show the zeroth order effect. Then you can refine this picture at will. All right, so it provides immediately the fact that K should be equal to 3kBt over Na squared, which is something we already obtained. It was the stiffness of the entropic spring associated with an ideal polymer chain. So this is the first tutorial. It can always be rewritten as kBt over A squared, which is the simple stiffness you can construct if you take entropy and a monomer size. And then you have a linear assembly of springs. So the stiffness goes with 1 over n when you are putting them in series. All right, so now K in this dumbbell, this elastic dumbbell picture, K is not random or unknown. It has to be correctly chosen. So dumbbell means halter in French. So it's an elastic dumbbell here. So K here, if you want your model to really describe a polymer, has to be taken to be equal to the entropic stiffness. And then you can recover all the equilibrium properties of a chain. All right. So now let us estimate the relaxation times in this process. You see immediately, so first of all, perhaps we want to write the equation of motion. Sorry. Let us write the equations of motion. So on one side, you have this guy who is moving, and on the other side, you have this guy who is moving. So you have two equations of motion, and I will place myself in the overdamped limit, because now we understood that beyond 10 minus 10 seconds, we really don't care about inertia. And so you have two equations that are coupled. You have an equation relating the damping of the second mass. There is this noise term, but now there is a new elastic contribution because the spring here is pulling back. So you have a force which is basically minus K R2 minus R1. So it's a restoring force. And you have the same for the other half mass. So with a certain damping coefficient, another independent noise, and you have basically the opposite force. And those are coupled equations, okay? So if I want to solve that, what I will introduce is the two relevant modes here, and I will introduce the sum, since they have the half mass, the same mass, I divide by 2, and this is simply the motion of the center of mass. I mean the position of the center of mass. That's 1 degree of freedom, and the second degree of freedom is the one we already introduced, which is the difference. So I'm simply putting the sum and difference modes here. And if you do so, you are able to rewrite the equation as you can see here. So if I take the difference between the two, psi r dot is equal to minus 2k r plus f2 minus f1. That's the first one, okay? And then if now I take the sum of the two and I divide by 2, I have psi r of the center of mass. Sorry, it's a COM, not CEO. We are not in a big company here. Up. All right. And well, I just do the sum, so I get f2 plus f1. Okay, and F2 plus F1, I can always call it F, which is the one of the first part of this tutorial. If you take two noises that have zero average and a variance that is delta correlated in time, you can show that the sum is the same. Homework, do it, it's pretty easy. And so you are back to the problem that we already discussed, which is the motion of the center of mass. Okay, now we wanted to add this, and this is the novelty. We are adding an internal degree of freedom, especially through this stiffness in the center. Okay, and so this is a problem. It's the problem of a Brownian motion in a fluid here with a viscosity that is inside xi, inside an optical trap or an harmonic potential, if you want, with a noise. Again, you can transform that into some force that has a zero average and delta correlated variance in time. All right, so to solve that, you will simply have to solve the Brownian motion in an harmonic potential. This has been done exactly, and I encourage you to have a read about that. So we don't really need to do that now. What we want to see is that there is a typical time scale associated to that. If you take the average of this equation, the noise terms will disappear, and so you have R and R dot here. So there is a natural time scale that pops in that we can define now. So the time scale associated to relaxation of the internal degrees of freedom can be called tau equals to up to a factor 2 psi over k. Okay, so the damping and the stiffness matters here. All right, and so let us now rewrite it. So psi is 6 pi eta R, and we don't know yet what R is, and K is 3 kBt. Let me just take it back from here. K is 3 kBt over Na squared. So if you want, this can be recast as long as R is equal to A to a certain exponent mu, okay? Depending on if you are dealing with the Zim model or the Raus model. In the Zim model, assuming ideal description, well, mu is equal to 1/2. In the Raus model, then mu is equal to 1, as we already discussed. And thus, you can always rewrite the time scale for relaxation of the internal degrees of freedom as a reference time scale, monomeric, if you wish, times n to a certain exponent nu. And u being, well, in the Zim case, is 1/2 plus n, which is 3/2. And in the Raus case, it's the power 2, because you are adding this guy to mu. And tau, let me write it here. It's 6 pi eta R being equal to A cube over 3 kBt. And this is the time scale. This is essentially, if I write it this way, times A squared. Okay, and so this is essentially D0, or 1 over D0. So it's the time needed for a monomer to diffuse over its own size. So it's really the relaxation of a monomer. This is time scale of the relaxation of. And what we are saying that there is an amplification factor. There is this reference, which is the relaxation of the monomer, but for the full chain of size n, the relaxation is much longer. It grows with a certain power of n being equal to 2 or 3/2, depending on the type of description or hydrodynamics we consider. Okay? So we can put orders of magnitude here, as we did previously. To do so, let us first estimate tau naught. What is it? We said that d naught is 10 minus 9, right? And A squared, A is 2 angstroms, so it's 4, 10 minus 10. So you have something like 10 minus 11, so it's 40 picosecond, if you wish, okay? Let's say 10 minus 11, it's enough. This is the typical time scale for relaxation of a monomer, and we knew it's a relevant order of magnitude for molecular time scale. Now, what is tau? And so we have two approaches. In the Z model, it is 10 minus 11 times n to the power 3/2, which is equal to, if you take n is equal to 10 to the 4 as usual, it's 10 to the 6, okay? 10 minus 11 times 10 to the 6, it's 10 microseconds, all right? And if now you take the Rouse approach, you have something like that. And then 10 to the 8, so it's more 1 millisecond. So you see, it's already, this is giving you an interesting feature. This is a molecular time scale. But as soon as you put some large numbers in n, the relaxation time of the inner degrees of freedom of your chain. So here, the time you need to relax some stress, for instance, on the scale of the full polymer chain, well, can be much longer. It can reach few microseconds and even millisecond timescales, which are really observable timescales. So a polymer is a very slow object in terms of dynamics. Okay. Now you have orders of magnitude that are interesting. Okay, so we know that there is some self-similarity in the description of a chain. And so this idea of having an elastic dumbbell, we just did the first order proposal where we have half of the mass on one side, half of the mass on the other side, and the string in between. But in fact, the whole chain could be modeled as an assembly of mass and springs. And so depending on what length scale you are considering, you will have a time scale associated to it. And so in fact, by the self-similar properties of your random walk, you can define the relaxation time tau p of a portion of chain containing p monomers. And this is again with nu being defined here, either 3/2 or 2, depending on the Zim or Rouse description. The important part is that now you can put any p you want. So it's interesting now, a polymer chain. First of all, it's an object which is kind of spherical that moves in a fluid. So you have the degree of freedom associated to the center of mass. But at the same time, inside it, you have different time scales for relaxation depending on what type of feature you are considering. If you have a little knot or stress between two adjacent monomers, well, it will be really close to tau knot. If you, in fact, have a change of conformation that implies the whole chain that you want the stress to be relaxed over the whole chain, for instance, I pull on the chain first and then I let it relax in the solvent, well, it will take a bit of time for that chain to go back to the coiled state, and then you will have capital N here. And for all the intermediate situations, you can have the formula here. So you have a hierarchy of timescales that was proposed by Rouse here. All right. Okay, so now we would like to finish by, this part, by discussing the clear picture of a solution, now a real solution, okay? So if you remember what we described, so we are going to semi-dilute solution. What we did previously, we said, okay, in fact, in a solution, you start to have chains that fill each other. So you have some kind of length scale that appears in the problem. We call that psi is not the damping coefficient here, it's the blob size. But let me call that, yes, let me change the name, it's not very good. So it's the blob size, LB. And in fact, we transform that problem into the following one. So a chain is in fact made of blob chains, of blobs. And in this blob, actually, you have only a portion of chain that fills solvent here as well, but no other chain. And you fill the other chains only every LB, basically. Okay, so that's another chain. And so you're paving your solution with those blobs. And so you end up with a melt of blob-like chains. So a semi-dilute solution are melts of blob-like chain. That was our conclusion previously. This allowed us to make the connection between the pure melt, where there is no solvent, and the dilute situation. And we had the crossover where every quantity was really renormalized. So that is for the static picture. There is no hydrodynamic, there is no flow. So now we are interested in time scale for relaxation. Well, the argument is central here, and is to say that, well, also for the dynamics, there is a LB that appears. It's a hydrodynamic blob, okay? But there is a certain time scale below which you don't feel the other chain, and below which there is hydrodynamic interactions. For instance, in this blob, now on the dynamic aspect, when everything is flowing, well, all the red molecules of the solvent here will be moving together with the chain. There will be hydrodynamic interactions, so they will move as a little bag of size LBH, okay? Blob length for the hydrodynamic aspect. And outside that length scale, meaning after LB, those quantities, they won't drag each other, meaning that the red molecules from the solvent here in this blob will not be attracted or will not move together with this blob. So we say that the hydrodynamic interactions are screened. Screened. Pretty much like the static ones were screened in the actual blob picture. On a length scale, LBH. And it happens, people have studied that LBH is very close to LB. So in a spirit of unifying everything, we can assume that basically the static picture is valid also for the hydrodynamic, and so that a chain is in fact a collection of bags that we call blobs. In each of those blobs, you have the Flory picture, meaning that the size of the blob goes like the number to the 3/5 times A. I'm thinking here about, let's say, a thermal case where the solvent is ideal. And outside, you have an ideal statistics. That's for the statics. And for the dynamics, here inside, you have the Zim behavior, okay? And on the long scale, you have Rouse. Why Rouse? Well, in fact, we say that the semi-dilute solution is a melt of blob-like chains, and we know that the Zim picture is for melts. So on the long scale, on the large scale, this is Rouse dynamics. So really, you have the same picture as before. In a blob, you have a chain with some solvent around. The chain first fills the solvent, so its statistics in terms of static properties is provided by the Flory exponent, a realistic exponent. And at the same time, when this sphere moves, it will drag all the molecules around, so it's the Zim dynamics for solutions. Now, on the long length scale, you have a collection of blobs that act as a melt, so the statistics is square root of the number of blobs. So the total size goes like that times the blob length. That's for the, sorry, I should have put that in black. Anyway, this is in black, okay, this is related to the statics. And the Rouse dynamics, because now you have a collection of blobs that are independent from each other. So when this flows at a certain velocity in a fluid, each of those rigid-like units will contribute independently of the other. So you are really summing the number of objects that have all a 6 pi A LB drag coefficient. Okay, that's the picture for the dynamics of a semi-dilute solution. Okay, so let us put numbers for that. And prior to that, I would like to refine the previous picture, because so far what I did if you remember correctly, for the Zim dynamics, let me just put it back here. As you can see here, I said, well, in the Zim proposal, the polymer is a chain here with solvent around. And so I said, it will move as a rigid object. So I took square root of n times the size of a monomer. Well, this is only valid in the ideal situation, not in a realistic chain. So I first want now to refine this picture and redo the Zim case, but for a proper athermal solution. So you have in a solvent, it's an athermal solvent, so that the free volume, the excluded volume is equal to A3 here. And the radius is the Flory radius. That's the radius of gyration, okay? So let me just take one chain in a solvent. It's dilute for now. So for this chain, the time scale for relaxation will be associated to the size over which I'm considering things. So I will take the radius squared divided by the Zim diffusion coefficient, right? So I want to estimate the time needed for diffusing over my own size, so R squared. And here, I will take the Flory exponent soon, but dz is what? It's d0 divided by n to the 3/5. That's what I'm correcting. Previously, I took 1/2 because I was not caring too much about the details between, or the difference between ideal and realistic solutions. That was not my point. Now, this is my point. I want to construct a proper and realistic description of the dynamics of a semi-dilute solution. So I want to be precise in what I call as a Zim dynamics here. So I put 3/5 here. And so this is n to the 3/5 to the power 2, a squared, and this is d0 n to the 3/5. So I end up with 9/5 times tau naught. So the time scale for relaxation in a realistic Zim picture is a monomeric time scale for relaxation as before, but the exponent is not 3/2, is in fact 9/5 if you are really exact on the spatial properties of the polymer chain. Okay, so that's just a correction from what I said previously, because now we are entering into first order description. Okay, so now let us build the complete picture for that dynamics. I will construct the dynamics inside the Zim blob, and then I will construct the full dynamics, considering that it is a Rouse-like dynamics for the ensemble. Okay, so let us consider what happens inside one blob. Inside one blob, I have tau blob, if you want, which is the Zim-like picture. So we just wrote it. It's the number of objects to the 9/5 times tau naught. The number of objects in a blob is called G. Okay, and G, remember, is connected to the size of the blob. So you have the size of the blob, which is related to the Flory exponent times the size of a monomer. And this is the number of objects. So this is basically, so those are, of course, scaling symbol. And so we end up here with psi over, or I mean LB over a to the 5/3 to the power 9/5. So which is LB over A to the power 3 times tau naught. Okay. Now let us connect that to the density. So the density is how much monomeric volume you have here divided by the volume of a blob. So you have basically G monomers, each contributing for A cube. And then you divide this by LB cube. Okay. And we know that G is equal to LB over A to the 5/3. So it's LB over A to the 5/3 minus power 3, which is minus 9/3. So it's LB over A. And this is exactly what we did previously for the static blob. So I go pretty fast here. My point is just to recover rapidly the fact that this is related to the density, in fact. Okay. So I can now plug that quantity here, and I end up with 9/4. So, as a conclusion, the timescale for relaxation of a blob at the scale of a blob is related to the density of monomers with respect to the solvent. And of course, there is a reference timescale. So let us look at the limiting situations. When phi is equal to 1, which is the melt, I have no solvent, only monomers. Well, I end up with the timescale for relaxation of a blob is a monomeric timescale, which is expected because the blob is a monomer, okay, in that static picture. So that is perfectly okay. And remember, when phi is equal to phi star, which is the onset of semi-dilution, then tau blob is what? Well, tau blob is phi star minus 9/4 times tau naught. And phi star is the density at the onset of dilution, meaning at the moment where you can pave space with individual polymer chains. So it's n times A cube over the radius of Flory to the cube. And so it's 9/5, and here you have fifths. So here tau blob is phi star, which is 4/5 divided by 4, so 9/5. So we recover that tau blob becomes n to the 9/5 divided by tau naught, which is exactly the Zim-like result. Okay, so we are really connecting the dilute regime and the melt regime as we did for the static picture, but now in a dynamic way. Okay, so that is the blob scale. So we know the blob scale. And let me summarize it. This is the good quantity. That's the blob timescale. Now, what about the chain timescale? Well, we said that we have a Rouse dynamics. So the Rouse dynamics, well, it's the power 2 of the number of objects times the monomeric timescale. Let me just show you it. So Rouse is the unit timescale multiplied by the number of objects to the power 2. The unit timescale now is a blob, and I have n over g blobs in this effective chain. And so this is the timescale for relaxation of the total chain. So it's n squared, okay. Tau blob is phi minus 9/4 times tau naught, and then I have g squared here, okay. And g we said previously, let me just find it back, g is LB over A to the power 5/3. And LB over A is phi minus 3/4. So G in terms of phi becomes minus 5/4. Okay, and thus n squared, 5 minus 9/4 divided by 5 minus 10/4 times tau naught, which says that at the end of the day, tau chain is, well, tau naught, that's interesting, n squared, that's also interesting, and then there is a correction depending on density, which is 1/4. And that's the final result. Based on that blob concept, we are able to find the relaxation time of a real chain in a solution with plenty of other chains. So it's a complex problem, but we say that basically it scales like the Rao's proposal for a melt, but there is a correction in density. In particular, we can recover the limiting case when phi is equal to 1, which is the melt. Well, of course, then the relaxation time of the chain is the Rao's case. The Rao's picture describes the melt. N monomers, each having an individual tau naught relaxation time. When we reach the dilute regime at the onset of dilution effect, then tau chain becomes tau naught, so n squared, and now we have to see what phi star is, and phi star, I think we found it recently, is n minus 4/5. So that's, sorry, that's phi star to the power 1/4. So this is tau naught. Then you have minus 1/5. So it's n 10 minus 1/5, which is tau naught times n5. And we recover the ZIM proposal as expected. So we are bridging the gap with this complete formula here between the dilute regime and the melt, and we have a result that makes only appearing the density of monomers. Okay, so now we have a complete picture for what is a solution of polymers, meaning with plenty of other chains everywhere. Huh? Okay, it's an assembly of blob-like chains. It's a melt of blob-like chains. We know what's going on inside the blob. There is no other chain here, and there are interactions, both static and hydrodynamic, with the solvent. And outside the blob, you screen those interactions out, and you are left with an ideal picture of a blob chain and a Rao's dynamics. And so you can, at every length scale, describe the relaxation time, and thus end up with the total relaxation time of your problem. Okay, so now you understand solutions pretty well. The very big step here that you have to keep in mind is this one. We identified the length scale for the screening of the static interactions, meaning the conservative potentials, van der Waals, for instance, or repulsive barriers and so on. And the length scale for hydrodynamic interactions, meaning if I move in a fluid, I will displace the fluid around, and this will move solvent molecules with me on a certain length scale. Okay, so this is related to the Green's function of the Stokes equation and so on. So identifying the two is in fact a good assumption. It's not an exact relation, but the orders of magnitude are very comparable, so it's a reasonable picture. But please keep in mind that it is the central assumption here. That's the main one. All right, so I'm done with the integral degrees of freedom. I think you have a broad picture now, and I would like to finish by the reptation model by Dejean. I won't do the total model. You can have a look at the paper I sent you. I will just do some scaling. So now what we consider is that each chain in a melt, so we are in a melt, is in fact surrounded by plenty of other chains. There is no solvent, and so finds itself into a kind of tube. It's an effective mean field tube that is created by the presence of plenty of other molecules around. So if you want, a polymer chain is constrained to move because you have everywhere other molecules, and so it has to move in a tube made by the neighbor. The mean field aspect assumes that this tube is fixed. It doesn't fluctuate. Also, the polymer chain is not fluctuating along the tube. Okay, there is no extension of the chain and so forth. Tube is fixed. It's a mean field picture. Refinements have been proposed numerically and theoretically to that, but we will just do the mean field here. And the idea is to say, well, inside this tube, the chain is diffusing around along the tube. So if there is, for instance, a stress that is created here, it will propagate by diffusion. So it can come back at the front and at the back, sorry. And so it just moves and comes back and diffuses. And at some point, the stress has been released outside the tube. And this is the moment where you can say that the time scale of relaxation has been reached. Okay. And so it's a much longer process than the Rouse one that we described so far. Let us see why. So first, it's a mean field description because we say that the tube is fixed. The neighbors are frozen, etc. The length of that tube, the curvilinear length here, is typically provided by the number of objects and their individual size. It's a polymer chain with n monomers, each having a length A. Now, inside this picture, we are dealing with a Rouse-like problem because we have monomers everywhere around, and we are really in a melt. So if we are in a melt, the Rouse dynamics works, and so the diffusion coefficient is basically something which is 1 over the number of objects. Every monomer is frictional, is damped by the neighbors, okay, in the Rouse description. And so the time scale for relaxation is immediate. If I write this, the time scale for relaxation is the length over which I need to diffuse divided by the diffusion coefficient, which is L squared A squared, and this is D naught times what? Times, what do we say, N here. So the time scale for relaxation is A squared over D0 times N cube. And this is what we call the monomeric time scale. So you see now the time scale for relaxation is again the monomeric reference, but the exponent on the number is huge. That's the reptation scaling by De Gennes. Okay. So if we again estimate the values, remember we had tau naught, which was 10 minus 11, I guess, and n is 10 to the 4, so 10 to the 12. So you see now the time scale that can be as large as several seconds and even minutes. So it's a very long process for a polymer chain that is entangled, that is very long and entangled with neighbors. This guy, to move, will have to slide like a snake, and it can take seconds. So now you understand why plastic materials, when you melt them, if you take your plastic ruler, for instance, to draw straight lines, take a lighter and burn it, it will melt. That object is so viscous that the individual polymer chains inside are all entangled. Okay, that's in fact the cause of the viscosity. And the relaxation of individual timescale is second-like. I mean, this is a timescale that is normally observed at macroscopic length scales. You would expect molecules to behave at timescales much smaller than the microsecond typically. Okay, so that's a very interesting reason. And this will lead to the amazingly slow dynamics of polymeric materials. All right, a final remark. Experimentally, if you try to measure the time scale for relaxation, for instance, by viscosity, with a certain exponent nu, what you will find is that nu is equal to 3.4. So it's a bit larger than 3. And this correction is in fact associated to the fact that the tube itself is a fluctuating quantity. The polymer chain is inside the tube, but the tube is made of other polymer chains that are moving, that are fluctuating. So you have fluctuation of the tube, and also the chain itself is fluctuating in these directions. So the tube also can extend longitudinally. So if you combine both effects, you can show that this leads to a fine correction of the exponent. But you got the main idea, and I let you have a look at the articles if you're interested in more details. All right, so it's time for me to conclude, and thank you very much for this year. It was a very difficult year due to this COVID crisis. I apologize for that, even though I'm not responsible, but I hope you could follow the Zoom lectures. I thank you for your very good questions, either during the Zoom sessions or also by emails. I mean, it was very interactive, I found. Please feel free to make me private comments on what was bad so that I can improve, because I don't know about the speed, I don't know about the voice, the microphone, the whiteboard. I mean, in particular, the writing is not very optimal. So please feel free to frankly give me all your suggestions in case the crisis would come back, which I don't hope. And with that, I thank you for your attention. Feel free to contact me if you have any question about the future, if you want to have advice to find a good spot for your PhD or for anything else. I'm available with my email that you. Thank you very much, and goodbye.